Some examples are our PPA in place with NV Energy in Nevada, as well as some interest from the GeoZone in California. So what actually is the Everloop technology and how does it work? It's a closed loop geothermal system that envisions drilling 2 vertical wells, which are cased in cement at depth. And then we drill out a radiator section. So we have multilateral, we call them legs, that move out sort of following along each other in a certain distance. And then we intersect at the toes. These are drilled open hole, but we seal them with a proprietary technology called rock pipe, which prevents any transmission of fluid in or out of the reservoir. So because it's a closed system and we're not exchanging fluid, we're working on a conduction-based system rather than convection. This also gives us a really neat benefit in what we call the thermosiphon effect. So because there's a density difference in the hot and cold wells, the system actually naturally circulates and it's able to operate without any pump, any parasitic load, and we can deliver more energy to customers. We have 2 different styles of design, our 1.0 and our 2.0 wells. The 1.0s are more of a horizontal multilateral section targeting a sedimentary basin, whereas our Everloop 2.0 is drilling down at more of an angle into basement geology. This allows it to target hotter, deeper rock and bring more energy to surface. So we have a really nice scenario where we're able to take a lot of the advantages of traditional geothermal. So we are able to provide baseload energy. We are able to operate around the clock. We don't have a ton of emissions. We have a very dense surface footprint, especially compared to other renewables like wind and solar. But we have a few benefits that we're able to, expand upon that some traditional or enhanced geothermal sources can't really. We don't need to look for a permeable aquifer, and we don't need to rely on fracking to sort of simulate one. We're looking for competent rock underground, which we believe is a bit more available and makes the technology a bit more scalable. I mentioned the thermosiphon effect removes the need for a circulating pump, so we don't have a parasitic power draw pulling away from what we can deliver to customers. With no fracking, we don't have to worry about interseismicity as well. And on top of that, because we're not exchanging water with the reservoir, we have very minimal water consumption in our process outside of the drilling process. There's very little actual water that needs to be added into the system over its lifetime, so a fairly low operational footprint as well. And lastly, because it's based on conduction, it's a highly predictable system. We're pretty accurately able to estimate how these systems are going to perform over their lifetime, what their output is going to be, and how that's going to change over time. A really big benefit that we've been investigating a lot this year is dispatchability. This is the idea that we control the output of the system by controlling the flow rate. So while we can operate in a flat baseload capacity, we can also adjust our output to match load curves based on other renewables such as solar in the area, or the time of day, ambient temperature, if our systems are sort of basing their efficiencies on those parameters. So the graph on the right is sort of an example of how we can shape that curve. We've actually been testing our dispatchability algorithms, which are based on machine learning at our test facility, Everlight. Everlight was our first demonstration facility built back in 2019. This was our first real chance to demonstrate our technology to the world. We had a couple key goals. The first was to prove that we could actually drill a well that we were proposing in the style that we were talking about. This involved 2 well bores that started 2.5 kilometers away at surface, went about 2.5 kilometers underground, and we had these open hole well bores approach each other and connect basically head on using magnetic ranging technology fairly off the shelf that's used commonly in other SAGD operations in Alberta. We didn't want to stop there. We pulled the drill strings back, kicked off a multilateral well bore and intersected that as well, proving that the well design was repeatable and that these intersections were possible. Beyond that, we also deployed our rock pipe system in the field for the first time outside of a lab test. We've had a lot of success with this as well. We actually found in the period progressing the completion of the well, the leak off rate of the system decreased over time. Right now, in the course of about a day, we see fractions upon fractions of a percent of the system's total fluid lost. So our operators have had very little intervention in terms of adding water to the system over its lifetime. The last big target of us was to validate the thermodynamics of the system, prove that sort of the models we developed and the math we were looking at was accurate and correct. And we had a lot of success with this as well. We had 2 different models we were comparing. One was based on pre-drilling knowledge, so our geological prognosis and other understanding of the formations. And then we did what we call the history match model, which was developed using inputs post-drilling. We found that the pre-drilling model was accurate to our field data within 5% and our history match model within 0.5%. And you can see the graph on the left here is sort of a tracking of our measured and predicted values over a couple of years of operation. On top of this, we've had a lot of third-party support to validate our thermodynamics. TNO, NREL, CFER are all examples of organizations that have done their own investigation into the methodology we're carrying and found a lot of agreement with what we're doing as well. Through our investing process, partners with a lot of subsurface experience like BP, Chevron, and OMV have had their experts through the due diligence process really get behind the hood in our modeling methodology and have enough faith not only to support it but back it financially and want to see these projects develop further. This was the first sort of example of proving our technology out. Everdeep was our next demonstration project. This was more of a Everloop 2.0 style well drilling into basement hard rock. This sort of rounded out our technology suite that we needed for a commercial scale project. So we demonstrated here, one of our big technologies was insulated drill pipe. The name is pretty much as it suggests. It's drill pipe that prevents the hot drilling mud in the annulus from transferring heat to the cool fluid inside. This allows us to keep the BHA really cool, and we can actually use off-the-shelf sort of normally rated BHA components in formations that are much higher temperature than what we're rated. So we had a lot of success with that. We tested our multilateral technology, so being able to kick off these wells in the same style that we're going to be doing at Garrett's Reed. We also tested our rock up again, this time in hard rock, and found similar successes to what we saw at Everlight. And beyond that, we've tested a ton of different BHA components, drill bits, etc. So going through to our first commercial 2.0 project, which will happen sometime in the future, we have a good data set of performance and understanding that we're going to be able to hit the ground running and really start off strong with that. So now this all sort of culminates into our project Ever Europe, or Garrett's Reed. So this project kicked off earlier this year. I know we have an inauguration event in July. Right now we've got 2 different drilling rigs on location that are constructing the first loop, as well as an ORC power plant that's being constructed between the 2 drill pads. So the total scale of this project is going to be 4 different Everloops, each with 12 legs. This is going to produce about 64 megawatts of thermal, 8 megawatts of electric, and provide heat and power to the nearby town. We'll start with power once the power plant comes online, and then they're building out a district heat network to the site. We're really excited to see how this sort of pans out. It's going to be a several-year operation. But what we're really excited about is actually the repeatable manufacturing style operation and of drilling these wells. So because we're drilling very similar lateral systems in very similar formations for the duration of the project, we're thinking we're going to see a lot of learnings, and from that sort of observe what we call the learning curve. This is something we see in all technology areas, especially with renewables, wind, solar, even traditional oil and gas has demonstrated that if you have a repeatable process and you continue to repeat it, your teams get more experienced, you find efficiencies, cost savings, time savings to dramatically improve the effectiveness of that technology. So we're already seeing this at Garrett's Reed with the amount of well we've drilled so far, where one rig will communicate to the other. Something it's observed, something it's seen, and optimization it's found so that that second rig can proceed through the same section with improved optimization and sort of be proactive in what it's experiencing. And we're thinking this is going to be even more evident when we get, really into the lateral sections of these wells, especially into the later loops. You imagine a single Everloop has over 72 kilometers of open hole wellbore. So it's an incredible amount of data that our team can utilize and learn from and work on improving these projects. And this sort of stuff will not just apply at the project level for Garrett's Reed, but we also think expanding out to all of our projects globally as we continue to get better at these. So that's sort of our update on our technologies and how our technology is progressing. So we're really excited to now finally bring it to the commercial scale and sort of demonstrate why it's ready for the global market.
A few words on green thermal. We are very new company, only about half a year old. But some of the technology I'll show you is actually from the oil and gas industry, developed over the last 2 and 3 years. Half the senior management in green thermal comes from the oil and gas industry. So what we're trying to do is take a lot of the well-known technology and put it into geothermal. We're a fully funded company, and we hope to drill our first well within the next 18 to 24 months, probably in Denmark with funding from the Danish government. So just a few words on the agenda. I'll just go through a little bit about background and technology. Then I'll talk about the dual rack performance, and that's the invention that we made that we think will make geothermal easier to extract from the earth. Then a few things about our subsurface requirements. How do we get successful? And then some applications here in Europe. You're probably very familiar with this, the conventional solution to geothermal right now, the doublet solution where you see very commonly used in both Munich and Paris especially, but in other locations as well. And that gives us a lot of challenges. So we have the reservoir requirements, porosity, permeability, how much reservoir sections do we have? We have the corrosion of the equipment installation, scaling in wells, fracking maybe to improve the flow, which induce seismicity and give you problems on the surface. You can pollute the water aquifers, or you can even have toxic waste, which we have an example of in Denmark, where we get radioactivity material with the production. So just like the previous presentation, how can we solve some of these problems? And again, we propose a closed loop solution as well. So if you see my pointer, so we drill down vertically, 2 to 4 kilometers, depends on the temperature in the specific area. And then we drill a horizontal section, 2 to 6 kilometers, again, depending on the output we want to have. So we circulate the water between the outer and the inner pipe, it goes down and is then heated along the horizontal section. And then here at the end of the pipe, it returns and then flows back up. So it's the horizontal section that gives a lot of the effect. That's where we're heating the water. But this is a closed system. So this tubing here is actually completely enclosed. So the water will not come in contact with the geology. Then often the problem we would then have is that when you return the water going up to the surface, you lose a lot of the heat. So that's why if we zoom in, so this is what you see here, is that the inner pipe here is actually double walled. And that has a continuous vacuum all the way from the toe of the well and all the way to the surface. So having a continuous vacuum means we only lose 2 to 3% of the energy on its way out, up instead of maybe 30, 40%. So that's a way we maintain a lot of the energy we're extracting. So we're trying to use standard oil and gas industry technology. So it's down here in the horizontal section is 7.5-inch tubing. The vacuum pipe is 4-inch inside and 5.5-inch outside. So in general, it gives about 1 inch of room for a vacuum. There's continuous vacuum all the way, and we can maintain that at the surface. So when we actually deploy the whole system, every time we install a new section, we will put on the vacuum. But if you later on need to re-vacuum everything, that can be done as well. So because of the siphon effect here, because you're pumping cold water down, hot water up, we don't have any downhole equipment at all. If we close off the system and want to restart it, we maybe need a very, very small surface pump, but that's all the equipment that's really needed. So some of the benefits that we see with this solution is that instead of the 2-well system, the doublet system, here we only have 1 well. I do acknowledge that, of course, having a horizontal section will make it more expensive to drill. There's less geological requirements. Again, we don't need to look at reservoir, certain porosity and permeability, but there's still certain geological settings that we want to look for, and I'll come back to that a bit later. It's very safe. There's no fracking of the reservoir. Well, it's impossible because it's a closed-loop system. There's no surface pumps or heat pumps, anything like that. So this is essentially a zero-emission system. Very flexible. We can turn off and on or adjust the flow rate as we want, which you can't do with a doublet system. Very easy maintenance. Whatever equipment we need, if it's a small vacuum pump or circulation pump, all that could be in a 20-foot container on the surface. And again, the surface footprint with a 20-foot container is extremely limited. Again, due to we don't need all the surface equipment. But of course, to this dual vac system, the vacuum system, there's some key parameters we need to look at. So that's the heat loss going to the surface. The thermal conductivity is very important. The length of the horizontal section, has an impact, and of course the flow rate. So just try and look at these parameters. A lot of the modeling work I'll show you here has been done by a Norwegian institute called IFE, and also verified both by OMV and Total Energies. So we start looking at the heat loss. What you see here is the vertical section is the length of the well. So the 9 kilometers long, around 4 kilometers, that's where it goes horizontal. And then you have the temperature on the x-axis. So what you see that if you take the blue lines after from 1 to 50 years, the water is slowly heated up. It starts at 45 degrees, slowly heated up along the horizontal section. And then we end at a temperature between 90 to 100 degrees at the toe of the well. And then in the red line, the water returns back. And that's where you see the return temperature is more or less vertical, meaning that we're only losing 2 to 3% of the energy. The other key parameter, which is very important, is the thermal conductivity. So here on the right, you have, again, up to 10 years, and you have the temperature and the output. And then you have different options here for thermal conductivity. So normally the rocks we will look at would be around 2.5, but of course I'll come back to 5 that correspond to rock salt, for example. So if we take the average geology of 2.5, we see we start around 160 degrees in the reservoir, and then as we start producing over time, it will actually drop. But even after 3 to 4 years, the temperature in the reservoir will actually be fairly flat and will stay just around 110, 20 degrees, more or less for the next 50 to 100 years. And if we convert that into output, of course, you have a similar curve that it will flatten around up by 2 megawatts. So we think these systems, again, because there's no corrosion, it's closed loop, could last from 50 to 100 years. So we have a very high CapEx, but a very low OPEX. Length of the horizontal section. So of course, one of the issues here is that we have a pipe 7.5 inch. So we have a limited surface area. How can we compensate for that? We could do that by drilling horizontal instead. Every time I present this, people get very concerned about these horizontal sections. But again, remember in the US, 70% of all wells drilled onshore now are actually horizontal wells. So there's nothing in the oil industry that wouldn't say that this can easily be done. So again, different examples, horizontal section 5, 3, 5, and 7 kilometers. And of course, the longer you make the horizontal section, the higher temperature you can maintain over time because you have a longer length of well to actually extract heat. And you see exactly the same pattern for the output in megawatts. So if we have a very short section of 3 kilometers, you see we end up with maybe only 1.7 megawatts. But if we have a very long horizontal section, we are at 2.5 megawatts. So that's one of the compromises we need to do when we drill a well, decide how long horizontal section do we need for a certain output. And then finally, the flow rate. Again, here are 3 examples, 2.5, 5, and 10 kilos per second. If we flow at a very low flow rate, we see that temperature over time would be more or less constant. And that's, of course, because the water passes through so slowly, there's plenty of time not to cool the reservoir because the thermal conductivity is so significant that there's enough heat to keep it going along. We are probably more looking at 10 kilos per second. And here we do see a drop. So this would typically what we would use for district heating. So find a reservoir about 110, 20 degrees, and then we'll be able to deliver around 90 degrees for this directly into district heating or district cooling. And again, here you see that we also, over time, get a much higher effect because larger amounts of water is circulated. So here, even though we keep a constant temperature, the output is actually very low when it's only 2.5. But again, that's a trade-off. Thermal conductivity and what kind of effect do we want out of the well and what temperature do we want out of the well as well. So as you can say, I said we are independent of the geology, like reservoir porosity, permeability, reservoir section, but there are still things that do impact how we can complete a well and how successful we can actually produce the ETIP. So the two main ones, of course, are temperature, but that's more or less a question of depth. But then, as I said before, thermal conductivity is very important. And we do see variations in the column of that. Heat capacity is also a thing to consider, but it's fairly constant, so I'll skip that one. And of course, subsurface requirements has an impact on drilling and completion requirements. I'll skip those as well. We do believe this is standard practice in the oil and gas industry, so we don't see any particular issues with drilling whatever rocks that we're going to encounter. But let's just look at the temperature. So really, the geothermal gradient. So these are numbers from northern Germany, Denmark, where we see sort of average, we talk about 30 degrees per kilometer. So that's normally what we're looking at. So if we want something for district heating, we are talking about 3.5, 4 kilometers depth, and then we'll drill horizontally. One thing to note, of course, is that there's a big difference in the temperature. So this is a map from Denmark at 3,000 meters. So you see where it's red, at least 105 degrees, but where it's dark blue, it's only like 75 degrees, like this northern tip of Denmark. And this does make a difference. So this is a difference of 30 degrees. So that would actually equate to another kilometer we have to drill. So it's worthwhile to find out where's the hotspots. And one of the reasons there's a hotspot here, of course, is there's a lot of salt structures. If we look at the thermal conductivity, again, these are numbers from Denmark and northern Germany, all the way through down to crystalline basement. So we see mostly ranges from 2.5 to 3, but of course there are some outliers like Lower Jurassic, in this case, 1.7. So that I would not want to complete my well there, the horizontal section. I would rather go down to like Upper Bunter sandstone. And of course, the one that really stands out is the Sechstein with 4.9. And a key reason for that standing out here is that because it has consists largely of anhydrite and especially of salt. And we know both of those have very high thermal conductivities. So that's one of the sediments or rock types I would really like to target with this closed loop system. So if you look at the geological settings, we divide them into 3. We have the normal sedimentary rocks, then we have the basement rocks, and then we have rock salt. So if you look at the sedimentary rocks, that was typically what you would drill for oil and gas or for water wells. So if you want a reasonable temperature around 100 degrees, you would drill 3 to 4 kilometers or 2 to 4 kilometers. So this is just a thickness map of where could we then implement a well. So we are really talking from sort of medium green and all the way up the color scale. So large parts of Europe, you see, would actually be able to find the right temperature. Especially here, again, in northern Germany and over here towards Russia, there's a lot of sediments to drill in. Basement, much more expensive to drill, I acknowledge that, but still, I think with the learning curve that was shown in the previous presentation, I think this can probably in the future be done as well. But there, it's really the whole Scandinavian, all the Scandinavian countries and over into Belarus, where we see there's a lot of basement rocks. And then there's certain parts down here in Europe as well. So this is probably not the obvious place to install a system like this, but I think over time, when we get better and better at drilling, it could definitely be a target. Oh. Then the last one, rock salt. So again, as I said, it has a thermal conductivity of 5 to 6. I know it's inverse of the temperature, but at the temperatures I would like to find, like 100, 120 degrees, it would probably still be around 5. Another nice thing about the rock salt is 2 to 3 times faster to drill than normal sedimentary rocks. So I can really see a good business case for that. So this is just a map showing all the salt structures. So there's a lot of salt in Europe, but it's really the salt structures where this would be easy to locate one or more wells. So you see, again, large parts of Poland, down into Ukraine, Germany, Netherlands, Denmark, there's a lot of options to place horizontal wells. So where, for example, in northern Germany, the duplet system would not be very good because you would get so much salt in your wells, you corrode the whole system. That's actually a benefit for our system. Then 2 minutes. So we are looking at sort of three different usage of our geothermal system here. So we're not looking at using heat pumps on the surface, and we're not looking at generating electricity. But even for that, we still think district heating, district cooling, and industrial uses, there's a lot of applications here. And we know that for district cooling, there's actually a larger need for district cooling than for district heating worldwide. So just one final example of if we had to do a district heating system. So if we took some kind of mid-sized city with 20, 30, 40,000 people, we would investigate how much power do they need, and then we would find out a site and then drill potentially in a star shape where you have 1 to 2 megawatts per well. So this system like this would give you 15 to 20 megawatts. And with that, I'll leave it over, hope for a few questions, and just remember that's a question I get very often, that it's completely closed loop system down here, and there's a continuous vacuum all the way from the tip here and all the way up to the surface. Thanks very much.
Ladies and gentlemen, good morning. First of all, thank you very much to ETIP to have us together with you today and introduce the latest we are actually doing into the advanced geothermal solution space. My name is Francesco Di Credico. I am the Global Sales and Commercial Leader for Geothermal within our new energies solution team that covers geothermal, but also CCUS and hydrogen. I'm based in Pescara, Italy, so it's a pleasure to be with you today. So we'll just go quickly through my slide. Unfortunately, we have to run a little bit, but I'll try to be very concise and effective. So I just want to be sure you have a nice and comprehensive understanding of what Baker Hughes is and what we are actually trying to do within the geothermal space. Baker Hughes is, I guess, pretty much well-known company with more than 100 years of history in the energy sector, obviously deep roots into the oil and gas E&Ps, but with at least 60 years in experience in supporting geothermal projects globally, worldwide. So the company has been changing a lot over the few years within, the organization, merger, acquisition, and separation. Just to make it short, the latest picture you see from our company is pretty much unique because we do have two big divisions within our company that can complement the subsurface solution for geothermal with the surface solution for geothermal that are actually referred to the energy solution part. Our profile is pretty much unique, and the philosophy we are delivering on a global scale in supporting geothermal project is actually complementing a support with any form in technology or services provision or partnering up or eventually co-develop fields for geothermal that can go from A to Z. So from feasibility studies to drilling of the wells to the production. So anything that comes within. Why we can do that? That's due to our current portfolio. As you can see from this slide here, we can really start from the simulation and the modeling of the subsurface. Understanding the subsurface is one of the critical aspects of the geothermal success for any project. And then, understanding what's going to be the most effective geothermal solution for this, how to drill the wells with technologies required. And then from the subsurface, we connect this with the surface with wellhead, trees, pipeline, turbines that are actually manufactured not too far from here in our manufacturing center in Tuscany, together with heat exchanger, turbo expander, and centrifuge pump. So we can really offer everything required for a geothermal project. What we have been doing specifically for the closed loop that actually fall within the advanced geothermal solution, I'll just go quickly here. So we are currently active in all the different geothermal spaces, starting from the district heating to the conventional geothermal, where you do have hydrothermal system, of course, for power gen and heating. We are supporting EGEC project, just to mention the Utah Forge in US. And we are also actively supporting advanced geothermal systems. So this is the new frontier, I guess, when it comes to geothermal. We have been listening, very nice presentation from the former speakers. Thank you for that. We are also actively investing into this space. We are trying to support this internally, but we decided to invest inorganically in this, in a company called Greenfire, based in California, that actually developed the Green Loop system. So it's a closed loop single well system that you see here on the slide. It's very simple. It's a coaxial concentric insulated tubing that is run in a hole. existing well eventually with a small pump on the surface if required, heat exchanger, and then depending on the temperature you get, you can use it for an ORC to generate electricity or eventually to distribute heat. It's a very simple system. It's a great game changer when it comes to existing fields that might be eventually converted or retrofitted within geothermal. So you think about the orphan oil and gas wells around the globe, or eventually those borderline subsurface regimes where you're probably looking at hot and dry environments, or eventually the fluids within the reservoir is very critical, is not easy to handle. So these are all the benefits from a closed loop system that are actually part of this new initiative we have been launching on the market just this year, actually last year, apologize me. So the initiative is called Well to Watts, and I guess the name is pretty much clear. So we do have a testing facility in Oklahoma City, proprietary facility from Baker Hughes. We have a test well. So we drill this small well. We can actually simulate downhole different conditions in terms of pressure and temperature, and we can test in the well closed loop solution. It can be the one we are actually supporting directly with Greenfire and Valurec, with which we have a commercial agreement. And we have several firms joining the consortium because they are interested in developing this technology. And I can mention here a company like Continental Resource, Chesapeake Energy, Impex, and the California Resource Corporation. It is a completely open consortium. Anyone interested can join, regardless the nature of his company, can be an operator, a technology provider, a research institute, really anyone that has appetite in developing or assessing the feasibility of this specific solution. And we are trying to test this equipment into this well. So I'll give you just a very quick overview. So you can see the picture here of the facility. You see the well on the left corner of the slide with the surface equipment on top. We do have also a small ORC now available on site that we can use to test the effectiveness of the energy produced. We actually been doing the commitment just a few days back, so it was October 11th. I guess we're going to share the slide, and eventually you can use the link to watch what's the latest in the space for the Well to Watts consortium. I just wanted to give you how the system looks like. So it's pretty much simple, obviously. Nothing new, as we said. We don't need to reinvent the wheel when it comes to geothermal, but we need to be very effective. So this is can be a really breakthrough and game changer for specific solution and settings, not everywhere. So we can simulate flow rates, pressure, temperature, working fluids. The available casing for the reservoir testing are 958, 7.5 inches, of course. Temperature up to 230 degrees Celsius. The pressure up to 350 bar. The flow rates can go up to 760 liters per minute. And, we have all the system and the sensoring to monitor the well real time and obviously do whatever analysis might be required. And you can see the well schematics here. So together with the well, we also have now this small RC, is a small one, it's 150 kilowatt power that can be used on site as provided by IECE. And we can perform, we can perform the test and getting all the results. We can analyze all the data acquired during the test and provide the full feasibility studies for the specific closed loop we might be willing to test downhole. Just to give you an update on the project, we have all this nice sensoring run within the hole with the fiber optics and cable and sensor, so we can really monitor anything everywhere. The RC is already there, the power cables. The wellhead has been installed in August, and we committed, with the first testing on October, so a month ago. And we are just working together, obviously, with Greenfire and Valurec in testing their proprietary green loop solution together. So we do have, obviously, additional plan to develop this closed loop pilot system. So we want really to accelerate the development and the learning curve from the system. Actually, the closed loop system from Greenfire, the green loop, are currently up and running in a couple of locations worldwide, talking about California and the Philippines. But obviously, we still have plenty of cases where we're trying to test this solution also in the different contexts. So as I said, it can be hot and dry, or it can be very aggressive reservoir fluid condition. So this is pretty much the essence of what we are doing with the Well to Watts initiative. So we are open to any parties that might have any interest in participating in this initiative together with us, or if you might have any project or any specific R&D initiative you would like to explore together with us when it comes to geothermal, just feel free to reach me out or reach out any Baker Hughes representative that you might already know.
Thank you, Francesco.